Hello everyone, my name is Chung, and today I'm going to go over the paper how to make a correct multiprocess program execute correctly on a multiprocessor by Leslie Lamport. So to go over this paper, first I need to introduce everyone to Chapter 7. Chapter 7 mainly focus on replication, which is to create a copy of the original database. The reason we are doing replication is because we want to increase reliability. So if the original data store is lost or corrupted, the replicate can act as the new one. And another reason is to increase performance. So we should put a replica near the where the user is so that instead of the user pushing off their workload onto the original data store that is far away, which increases latency of them getting the data, they can just access the data on their replica instead. So, but the problem with replication is inconsistency. When a user write data onto the replica, how long does it take for this data to be pushed and replicated on all the other replica data store? And also, when should this update begin? Should it update immediately upon the user finish writing the new data onto the replica? Or should this update be pushed after all the other replica has finished their own processes? So to help with this, we introduced the notion of a consistency model. Consistency model act as a contract between the process and the data source so that as long as everyone follow a particular rule set out by the system, everything works correctly. And in this presentation, we are going to focus on sequential consistency where the result of any execution is the same as if the operation by all processes on the data store were executed in some sequential order, and this order is specified by our program. So let's see how this paper defines and introduces it to us. So the book starts with a problem that accessing a single memory location in a multiprocessor is traditionally assumed to be atomic, but we know that this is incorrect as in a multiprocessor, there is multiple processes and operation that is running concurrently with each other. So synchronization commands are needed to make sure that the program runs correctly. And some of the method that was proposed before to achieve this synchronization is to use a constraint style of programming specific to a particular type of multiprocessor architecture, or another method is to reason about the program in a mathematically abstraction of the architecture. But instead, our author want to derive the synchronization commands from a proof of correctness of a particular algorithm. By doing this, he doesn't need to assume atomicity, which is difficult to find where the assumption is needed because if we just assumed it at the beginning, we don't know if there's part in the proof that doesn't need it at all. So let's see how he does it. So let's start here. We can see that the author represents the event operation as follows. So it can be either A straight arrow B, which every event in A precedes every event in B, or A dotted arrow B, which only some event in A precedes some event in B. He has also given us the 6 axiom that always hold true for any operation execution A, B, C, and D, right here. And we want to prove it with this algorithm right here. So in this algorithm, which is for a specific process I, before entering its critical section here, this process I must first make its xi to be true, and then check if x of another process called J. So Xj is false for Xj is false. This makes sure that mutual exclusion is guaranteed. So using the example here and the axiom he has given above here, using this proof here, he has able to prove his particular theorem, which is that there is a mutual exclusion between the execution of the critical section of process I and the execution of the critical section of process J, which means that either I execute its critical section first before J or J do it first before I. They cannot execute concurrently. One has to be before the other in all cases. And from this, the author is able to conclude this property. First is that if the value obtained by a read A issued by a process I is the one written by process J, then the value is the one written by the last issue write B in the process J, so that some event B process some event A, which means that in our process J, we do a write operation called B, and then in the next process I, we have an operation called read A. If they read a value from the process J, that means that some write operation B in J must proceed some read operation A in I. The next property is that if operation execution A, B, and C are issued in that order by a single process, and B is synced, then A, O event A, proceed O event C, which means that if we have three operation A, B, and C in that order in a single process, if B is synchronized as the middle one, then we know that all operation in A must proceed all operation in C. And finally, the third property is that a read of a memory cell that resides in processor cache proceeds every operation execution issued by the subsequent by the same process, which means that this read operation that we are doing must come before any other operation that is called later on by the same process. All this, as we can see, shows that operation must be in a specific order. A particular operation first, then another, and another. And they form a particular sequence that every operation must follow. And this is what sequential consistency is. My opinion with sequential consistency is that of course this leads to our eventual understanding and defining it as sequential consistency. Sequential consistency is easy to understand as it is a rule that all operations just need to follow a particular operation, always follow that ordering. So it's easy to understand and is still used in some model like C++ with its atomic operation or Go programming language because it has a strict following of a particular order of operation. It is hard to implement as there's some trade-offs such as a node with a progress that is currently in an order, but there are multiple other processes that is still above this process we are trying to run, then there may be some latency before our process actually run and finish. The second is that implementing and maintaining a system like this is more complex than a weaker model. So with that, I have some questions, which are there any other models that have less of a trade-off than sequential consistency? Also, how prevalent is sequential consistency being used right now? Because of its trade-off, how prevalent is it being used as the default model instead of another model? Thank you everyone for listening.